Hello everyone, welcome to this presentation. In this talk, I will study the linear model under the Federated Data Analytics framework. My name is Xubo. I'm a student from University of Michigan, Ann Arbor. This work is jointly done with my advisor, Raed, and also my collaborator, Anna, from Purdue University. The smart and connected systems, also known as IoT-enabled system, are transforming the computation and redefining the industry. In the traditional IoT-enabled system, there are several physical system components, and there are also several sensors installed on those components to real-time collect the data from the environment. And afterwards, those components will share the data with a central server or a cloud via the wireless network. And afterward, the server will analyze those data to make smart decisions. Here, let me provide you one more concrete example. Let's suppose there are several vehicles on the road enrolled in the teleservice system. There are usually several sensors installed on each vehicle to collect the condition monitoring data from each vehicle. And those vehicles will transmit all those data to a central cloud or to a server. The server will analyze those data to keep the driver informed about the health condition of their vehicles. Although the framework of IoT-enabled system is promising, it faces several challenges. First, the data sizes are usually very large. As the number of samples grow, the data sets might far beyond what any server can store in many real-world applications. In fact, based on a report from Statistica, it predicts that by year 2024, data produced on the edge, such as mobile phones or computers, will reach more than hundreds of zettabytes. While the global central server only has around 10 zettabytes of the storage. Therefore, transmitting and store all of this data is not feasible. Second, there is a significant storage cost. Even if one can store all those data on a central location, running a big model such as a neural network will cause very significant carbon emissions, which is not environmental friendly. Third, there's a communication bottleneck. For example, several devices or vehicles usually have a poor internet connection or have limited bandwidth. Therefore, transmitting all those data real time is not practical in many applications. And finally, there's also a data privacy concern. In fact, based on a report from Canada, many Canadian drivers who refuse to enroll in the automobile telematic program demanded that their personal driving data, such as their driving habit, should be respected by the vehicle companies. And they should have their own ability to control what data should be collected and what data should be shared with the central server. All those things impose a huge challenge on the traditional IoT-enabled system. Fortunately, in the modern era of computing, the computation power of edge devices is steadily increasing. For example, the Tesla autopilot system has around 150 million times more compute power than the Apollo 11. And also, our daily use smartphones now have the computational capacities comparable to laptops. Therefore, we want to exploit the edge compute resources to process more of the user's data where it is created. And this brings up a new data analytics framework, which we entitled Federated Data Analytics, or FDA. The idea of the FDA is actually very simple. We exploit the computational resource at the edge. We bring the computation tasks from the server to the edge devices. Edge devices perform computations and only share a very minimal amount of information with the central server. As you can see, this framework overcomes many aforementioned challenges, such as a privacy concern, as we no longer need to share the data with the central cloud. It also further reduces the storage cost and also the computation burden of the central server as we bring everything to the device. Therefore, the Internet of Things is on the verge of transforming from a traditional IoT to the Internet of Federated Things. For more information, please refer to our recent published paper, the IOFT, for more information. Now, let me present the idea of the FDA. Let's suppose there's one global server, and there are also K local edge devices, such as automobile vehicles. The goal of FDA is to solve the following objective function, where PK is a weight coefficient and FK is a local loss function. The most fundamental algorithm to optimize this loss function is called federated averaging, or FedAvg. So here I give a very simple example of the FedAvg algorithm. Let's suppose we only have 3 devices, which is vehicles on the road. Also have one data center or a central server. At the beginning, the central server broadcasts a global model parameter theta to each edge device. After receiving those global model parameter, each edge device will run some local computations to obtain their own updated parameters theta 1, theta 2, and theta 3. And then they send those parameters back to a central server. The server will then aggregate those parameters, for example, taking the weight average of the model parameters. And afterwards, the central server will rebroadcast the global model parameter to each device. And this whole process is known as a one communication round. I usually will iterate for several communication rounds until convergence or some exit condition is met. This algorithm briefly summarizes the FedAvg algorithm. Here, the C is a communication round. At the beginning of each communication round, the server selects some clients by the probability PK and broadcasts a model parameter theta. After receiving the theta, each device will run some local computations, such as the stochastic gradient descent, to obtain the updated parameter theta k. And then they send the theta k back to the central server. The server then aggregates all those parameters. I repeat this procedure several times. During the past few years, tremendous work has been proposed to improve the performance of FDA algorithm. In spite of some recent advances in FDA, most literature unfortunately focuses on the deep neural networks. Actually, to date, very few papers have delivered a federated treatment of the traditional statistical models. In this paper, we study one of the most fundamental statistical models, which is known as linear regression. We believe linear model is very important and is widely used in many real applications. Besides that, linear models also facilitate hypothesis testing, uncertainty quantification, and also variable selection. Therefore, we believe linear model is a very good starting point for the FDA algorithm. To this end, we develop an FDA treatment for linear regression with Gaussian noise. Our treatment is built upon hierarchical models, which allow borrowing statistical knowledge across groups or devices in the FDA framework, which I will explain more in tuition in the following slides. And finally, we validate our methods on a range of real-life applications such as variable selection and condition monitoring. Before getting started, let me first introduce some notations in this paper. Let's suppose there are K edge devices, and there's a central server that is connected to all the devices. For device K, the data set is given as a dk, which should go to xk and yk with nk observations. And we also assume that the dimensionality of the input space is d. Each device K is fitting a linear regression model parameterized by the theta k, which can be summarized as follows. The distribution of the yki can be written in the normal distribution with the mean x transpose times theta k and the variance sigma k squared. In this expression, the yki is an ith observation for the vector yk, and xki is an ith vector in the matrix sk. And theta k is a model parameter, and sigma squared k is a variance parameter. And for the sake of compactness, we denote by the big theta as a vector for all of the theta 1 to the theta k, which means this big theta contains all the device parameters. Here, let me start by presenting our first hierarchical model structure, which I will call it HM1. This figure, as you can see, the big square represents device K, and this small square represents the ith observation within the device K, where the X and the Y are our data point, and theta K is the model parameter. Here, we assume the big theta, which contains all device parameters, are generated from a matrix normal distribution with a mean 0 and also the column covariance big omega. In essence, the HM1 establishes a shared representation by defining a structural prior over the big theta. Here, this prior is parameterized by the omega matrix, which is a k by k cross-covariance matrix. This omega encodes a belief on the parameter generating distribution. Therefore, the big omega acts as a graph on the server that encodes a shared representation among k devices and facilitates information sharing. Mathematically, we impose a prior on the theta such that the theta follow a matrix normal distribution with the following parameter. Here, the big omega represents the column covariance. By the base rule, we can obtain the negative log likelihood function of the theta, which is the product of the prior and data likelihood. And by some algebra manipulation, we can obtain a loss function for the parameters, which is as follows. Therefore, our goal is to find the maximum posterior or MAP estimator of the big theta and big omega that minimize the loss function, which means we want to find the argmin of this loss function. Now, by taking derivative of the loss function with respect to big theta, we can obtain the following gradient. However, this term faces two fundamental issues. First, the central server does not have the data, which is xk and yk. Therefore, the server cannot run the gradient descent on the central server. However, if we broadcast this optimization gradient into different devices, we also need to broadcast the big theta and the big omega with each device, which violates the privacy constraint because the big omega encodes the relationship among local edge devices. To overcome this issue, we break this gradient into two stages. One is in the red part and the one is in the blue part. At the first stage, each local edge device will run a local gradient step, such as a gradient descent or stochastic gradient descent. And after several steps of the local gradient steps, we will obtain the updated parameter theta k, and then at stage 2, we'll perform a prior shrinkage on the local device. Here, the central server only need to share the aggregated information, which is summation of the product of the theta I and also the big omega. As a result, the central server no longer need to broadcast each components in the big omega. Rather, they only need to broadcast the compounded information of the theta I and the big omega, which will preserve the privacy information from each local edge device. Now, let me talk about the updating scheme for the big omega matrix. Here, attach the expression for the loss function. As you can see, in this loss function, it's not convex with respect to the big omega because of this log determinant term. Existing work from Zhang suggests to ignore the non-convex term log omega and add a convex constraint such as a trace of the big omega equal to 1. This term mainly regularizes the complexity of the big omega matrix. Afterwards, they provide a closed form updating scheme for the big omega matrix, which expressed as follows. However, This updating scheme usually faces computation issues such as a singularity problem, because we directly update the big omega matrix without retaining any old information from the big omega. In this case, we have a very high chance that the big theta transpose and theta may not be positive definite. As a result, the overall big omega matrix may not be positive definite. However, we can find a key observation. This expression, the big theta transpose times theta, encodes the information of device covariance. Therefore, we propose a new updating scheme based on this observation. Here we update the big omega based on the convex combination of the omega from the old iteration and also this information matrix. And the degree of the combination is controlled by this alpha. As you can see, as alpha goes large, we directly update the big omega using the information matrix. If alpha is small, we maintain the old information from this big omega matrix. In essence, this updating scheme prevents an abrupt change in the big omega, which is controlled by the alpha parameter. And this scheme also safeguards against numerical issues such as a singularity. Here, we summarize all the formatting procedures in the algorithm 2. At the beginning of the communication round, the central server broadcasts the column of the big theta, which is the theta k. And after receiving the theta k, the local device will run 2 stages of optimization. The first stage is called the local SGD or GD steps, which is simply run a gradient descent with respect to the data xk and yk. And afterwards, it will run the prior shrinkage step to update the parameter theta k. And finally, after receiving all the updated parameters theta, the server will run a procedure to update the big omega matrix. And we will iterate this step for several times until convergence. So far, we have presented HM1 that exploits the relationship among devices to improve the prediction performance. However, HM1 faces 2 limitations. First, HM1 only provides a point estimation of the big theta. As you can see from the previous slides, they only return the point estimation for the theta. And second limitation is that the big omega only encodes information for the k training devices. In other words, if you have some new incoming devices, HM1 cannot provide any borrowable information from the new devices. To overcome the limitation of HM1, we propose another hierarchical model structure, which is called HM2, that is based on distribution assumption. Let's start from this figure. Recall that the big square represents device k, and the small square represents the observation I, and theta k is a model parameter. Here, I introduce a global latent variable phi that contains parameter mu and also tau. And I further assume the theta k contained on this phi follow normal distribution with a mean parameter mu and variance tau times the identity matrix. As you can see, this assignment indicates that all the theta k are related and are generated from the same distribution. Yet the degree of the model similarity is controlled by the variance parameter tau. For example, if the tau is very small, it means the variance of a normal distribution is small. In this case, all the theta k are similar, and we can then infer that the data distribution among all the devices are probably homogeneous. On the other hand, if tau is large, it means the theta k are very different among devices. In this case, we can infer that the data distribution among all the devices are heterogeneous. In an extreme case where tau goes to infinity, it means theta k are very different and the devices are probably not well related. In this case, we prefer to use a separate modeling approach rather than the FDA framework. Now, based on the HM2 structure, we can write down the joint posterior of theta k and this global variable phi, which has the following expression. Here, the p phi is a prior over the phi, and the pyk is the data likelihood, and the p theta k is a prior on the theta k. In practice, it is sufficient to learn the posterior of the phi, and afterwards, we can infer the posterior of the theta k based on this phi information. I will provide more details later. Overall, our goal is to learn the posterior of this phi, which has the following expression. As you can see, HM2 has two unique features. First, HM2 helps you automatically define a prior over the theta k. Remember that we learned the posterior of the global variable phi that contains a mu and tau, and mu and tau defines a prior over the theta k. This indicates that we learn the prior of the theta k using the data, and we let the data speak itself. This demonstrates the key advantage of HM2. The second feature of HM2 is that we can quickly adapt the parameter optimization for an incoming device. Let's suppose we have newly incoming device theta k plus 1. As we have learned the posterior distribution for the phi that contains mu and tau, in this case, we can directly sample from this normal distribution and set a sample parameter as the initial parameter for the device k plus 1. And this feature is very similar to meta-learning, where we want a fast adaptation. Let me give you one example for the HM2. Let's assume each device is fitting linear regression parameterized by theta k with a dataset xk and yk. The one possible formulation for the HM2 can be as follows. Here, the yk given the parameter theta k and also the global latent variable phi follow normal distribution with the mean x transpose theta and the variance sigma k squared, which is the standard linear regression formulation. And then we assume the theta k condition on the phi follow a normal distribution, which is with mean parameter mu and also the variance parameter tau1 to tau d. Here, the phi equal to the collection of all the mu and all the tau. We then impose some prior on the mu and tau, which we, for example, just impose a standard normal distribution for those parameters. So one question is, how can we perform inference for the posterior distribution? In statistics, the most intuitive way is to use the MCMC methods. Let's take the Gibbs sampler as one example. At the beginning, the device 1 needs to sample the theta 1 from the density theta 1 conditioned on all other theta and dataset. Afterwards, it will transmit all those samples back to the central server. The server will then get its pros parameter and send it back to the device 2. Then device 2 will sample the theta 2 from the distribution of theta 2 conditioned on theta 1 till the theta k. And we will repeat this procedure for several iterations. As you can see, the sequential nature of MCMC is very inefficient. In many real-world applications of the FDA, we usually have thousands or even millions of devices. Therefore, the sequential nature of MCMC is very computationally inefficient. Furthermore, even if one can parallelize the MCMC into different devices, the number of samples required for the Gibbs sampler may increase significantly due to the curse of dimensionality. To overcome this limitation, we resort to one of the most popular approximation inference algorithm, which is called expectation propagation, or EP. Let me start with a centralized expectation propagation algorithm. Let's consider posterior distribution with the independent data points, which is a pi phi proportional to the prior of the phi times the likelihood for each data point. The idea of EP is to approximate this pi phi by an approximation density q phi such that each likelihood in this posterior is replaced by the qi phi. In other words, we approximate this blue term by this red term. The procedure of EP is actually very simple. Let's assume n equal to 2, which we only have 2 data points. Here, the top one is the true posterior, and bottom is the approximate posterior. The EP first takes an approximation factor Q1 out of the current approximation Q5 and replaced by the true factor, which is a true likelihood function. Then we obtain a new approximation function, which is called Q nu phi. And this resulting new density Q nu phi can be used as an updated approximation posterior. I will repeat this procedure for several times. As you can see, the EP can be very naturally extended to the FDA scenario. Let's recall that the original posterior for the phi can be written as follows, which is the prior times the product of the FK phi. The main idea of the EP is to approximate those FK phi from each local device by the local approximation function QK phi for k from 1 to k. And more specifically, we have the following formulation. Here we approximate the blue term Fk by the red term Qk phi. This page summarizes the procedure of the federated expectation propagation. Here, the Q phi is a global approximation function, and P phi is a prior over the phi, and Qk is a local approximation function. At the beginning, the EP removes the impact of the Qk from device K and create a term called cavity distribution. And afterwards, it adds a true likelihood function Fk into new approximation and result in a term called tilted distribution. Afterwards, it computes the updated posterior approximation, which by simply set the Q nu equal to the tilted distribution. And then device K calculates the change in the local approximation by taking the ratio of the Q nu over the old approximation Q phi to obtain delta Qk. And then all the devices send a delta Qk back to the central server. The central server then aggregates those changes in the Qk by taking the product of all the Qk. As I mentioned before, HM2 can be explained from a meta-learning perspective. Here, let me provide more details. Actually, the estimated posterior density Q phi encodes the crucial information across all the devices. Therefore, one can exploit this information for a new device to achieve fast adaptation. Let me give you one example. Suppose we have a new device K plus 1. Then we can sample the theta K plus 1 from this posterior density phi that follow normal distribution with the parameter mean and tau. We can set this sample as an initial model parameter for a new device. And this achieves the purpose of meta-learning. Now this algorithm summarizes the federated EP algorithm. As I mentioned before, we need to calculate the cavity distribution and the tilted distribution. Now we use this tilted distribution as a new approximation for the posterior. And we calculate the change in the Qk and send it back to the central server. Central server then aggregates all those change of the approximations, and we repeat this procedure for several times. After we obtain the approximation Q phi, we can further estimate the posterior of the device parameters. Specifically, by some manipulations, we can get the posterior density for the theta k, which as follows. Therefore, we can resort many sampling methods that is coded in the R or Python library to learn the posterior density for the parameter theta k. And using this posterior density, we can do the hypothesis testing, quantify the uncertainty, or provide other model parameter inference. And finally, let me talk about the application of the HM2 to the variable selection problems. The variable selection is one of the most important research fields in statistics and data science. As I mentioned before, In the hierarchical model, the key advantage is that we can borrow information from each other. Therefore, we want to ask, is it possible to let the devices exploit the shared representation structure to perform variable selection? Some previous work summarized the Bayesian interpretation of the variable selection models. Inspired by their work, we can impose a prior on the device parameter theta k such that theta k conditioned on phi follows some distribution with the parameter lambda and sigma square. Here, lambda is a regularization parameter, and sigma square is a variance parameter. We have several options for this distribution pi. For example, if we set this pi to be a Laplace distribution, then we can recover the lasso regression. And similarly, we can also recover many variable selection models, such as a ridge regression or group lasso. Now, let me provide some empirical analysis on HM1 and HM2. In our first simulation, we create k equal to 100 devices, and the input dimension is 8. We randomly generate a positive definite matrix big omega, and we use this omega to generate device parameters and also generate data for each device. For the first case, we assign 200 samples to each device. Overall, this generates a balanced sample size scenario. In case 2, for the first 30 devices, we only assign 20 samples to each device. And for the remaining 70 devices, we assign 400 samples to each device. Overall, we create an imbalanced sample size scenario. We fit 8 dimensions linear regression models using algorithm 2 to learn the device parameter theta 1 till theta k. And afterwards, we use the device parameter to perform prediction. We summarize the results in the following table. We report the average RMSE or ARMSE for each method. In this table, the separate approach means we model the linear regression on each device separately without communication. For case 1, as you can see, because all devices have a large sample size, in this case, the separate modeling approach actually works well. However, for the second case, because the first 30 devices, they have very few amount of data, in this case, the separate modeling approach has a very high testing error. However, our algorithm 2, on the other hand, generates a very small testing error. This is because in algorithm 2, we use the HM structure to borrow strengths from other devices. Although the first 30 devices have very few amount of data, we can still borrow strengths from the remaining 70 devices that has a rich amount of information. In essence, this result demonstrates the advantage of the HM structure where each device can borrow the strengths and information from other devices to train a better model. In this figure, I plot the convergence results for our algorithm 2. Here, the theta hat represents the estimated parameter, and theta star represents the true parameter. As you can see, our algorithm converges very fast. For the case 1, where we have balanced sample size, we usually converge within 20 communication rounds. And for the second case, even with the imbalanced sample size, our algorithm still converge within around 40 communication rounds. Overall, our algorithm is fast to optimize. Next, let me show the performance of HM1 on a real-world case study, which I use the NASA dataset. We consider the condition monitoring data generated from the NASA simulation tools. Overall, there are 100 engines, and each engine has 24 sensors that collect the time series signals real time. In this dataset, the input is time, which is one dimension, and output is a sensor signal. For each engine, I split the first 60% of the signal as a training dataset, and the remaining 40% of signal as a testing dataset. Our goal, therefore, is to predict the sensor signal trajectory on each engine using HM1. And the model I use is a polynomial regression model with 6 dimensions. This table summarizes the results of our model and all other benchmark models. Here, I compare HM1 with a separate modeling approach with FedAvg, and also with the state-of-the-art personalized FDA algorithm Ditto. As you can see, our algorithm outperforms all the benchmark models, especially the Ditto algorithm, which is widely used to train a neural network. This result also demonstrates that if we naively plug in the FDA algorithm for neural network into the statistical model, it usually generates a worse performance. Next, let me also provide some empirical analysis on the HM2. Specifically, we test the variable selection performance of HM2. Following the examples from the OneERP in 2019, we create several simulation cases below. In case 1, we have 10 devices, and we set the true parameter as follows. And we use those true parameters to generate data on each device. Each device has 100 data points for training and 1,000 data points for testing. For the case 2, I use the same setting as the one in case 1. The difference is that for the first 2 devices, I only assign 20 data points. But for the remaining devices, I assign 200 data points. This again creates an imbalanced sample size scenario. For case 3, I create 20 devices, and I set the true parameter to be the following. And each device has 40 observations for training and 400 observations for testing. Recall that in HM2, we obtained the posterior distribution for the theta k. Therefore, I can calculate the 95 confidence interval for the theta k. If the 95 confidence interval for a certain component in theta k covers 0, then I will select this variable out from the theta k. Otherwise, I will keep this variable. This figure summarizes the performance of variable selection for case 1, case 2, and case 3. I use the lasso as one example for the HM2. As you can see, first, our model creates a very small average RMSE across all the cases. And also, from second column, you can see our model has a very high crack inclusion rate, and we have very low false inclusion rate, which means HM2 works well on the variable selection problems. As I mentioned before, one advantage of HM2 is that it can quantify the uncertainty in the parameter estimation. Therefore, our final goal is to test the UQ performance of HM2. Here, I generate 100 devices and then generate device parameter as follows. I then use the theta k to generate 100 data points for each device k, and here is our HM structure. Using the algorithm I present in HM2, I calculate the posterior distribution of phi and plot the mean and 90% confidence interval for each component. And this figure summarizes the UQ performance of HM2. In this figure, the red dot represents the true parameter, and the black dot represents the estimated parameter. And the range represents the 90% confidence interval. As you can see, the 90% confidence interval of our estimated parameter actually covers the true parameter in most of the cases. In conclusion, HM2 provides a very good UQ performance. In this paper, we propose the FDA treatment for linear regression by adopting the idea of HM. We test our framework on a range of simulated and real-world data sets. Our models are easy to implement and fast to optimize. Notably, our proposed FDA algorithm also outperforms many widely used algorithms for neural networks. This demonstrates that for statistical models, our FDA algorithm can clearly perform better. Therefore, we argue that our model can serve as competing benchmark models for future development of the FDA algorithms. Thanks for attending this talk. Please let me know if you have any questions.